So without further ado, I think we're going to get started. So, this webinar is about getting started with running Apache Spark on Kubernetes. A few words about me. I'm the product manager for Ocean Spark. Prior to joining Spot.io, I was the co-founder and CEO of Data Mechanics, and Data Mechanics was acquired. So that's how I joined Spot.io. I've been working with Spark as an infrastructure provider for many years because prior to Data Mechanics, I was a software engineer at Databricks. And really just at a high level, our goal at Spot.io, at the team I'm working with, is to deliver fully automated and optimized Spark on Kubernetes. So this is why I'm giving this talk about Spark on Kubernetes. I really think it's the future of Spark, and there are many reasons why everyone should be excited by it. But there are also, challenges that we need to face, to overcome, to be successful with it. So the first section is we're going to do an introduction of Spark on Kubernetes. What is the architecture, the benefits, how does it compare to the other deployment model of Spark? Spark is a distributed analytics engine for big data. So it's a technology that helps you run code in a distributed fashion on many machines at the same time so that you can process large volumes of data. So typically, you start using Spark once you process volumes like hundreds of gigabytes or potentially terabytes or potentially petabytes of data. Usually that data is stored in an external system. Like in the cloud, what's most popular are the data lake, typically the object store, S3, GCS, Azure Data Lake. Data warehouses are also popular, like Redshift, Snowflake, as well as consuming data from streams or from any kind of external storage system that's supported by Spark. You're going to type your code in actual Python or Scala or SQL language. And what makes Spark popular is that it's also very versatile. So the main use case around Spark is typically batch ETL pipelines, but streaming real-time pipelines are also popular, as well as higher-end use cases around, for example, machine learning and data science, or business intelligence and interactive data exploration. Yeah, I mentioned it before. You're going to type your code, for example, in Python, and then Spark is going to figure out how to break it up into individual tasks that can be executed in parallel on many nodes. So you see that Spark runs on the cluster where you have multiple nodes, and there's a driver, which is the brain of your application, and then many executors. What Spark does not do is manage the cluster itself. For that, it needs a cluster manager, which we also sometimes call scheduler. And this is where Kubernetes comes in. Before Kubernetes, the main cluster manager was standalone mode, which is built in Spark but doesn't have many functionality. There is Apache Mesos, which was pretty popular at once but has been deprecated. And there is Hadoop Yarn, which is really the most widely used scheduler. But now Kubernetes is the new kid in the game, and it's really the most popular among new deployments because some of the benefits that we are going to see next. Before we dive into Spark on Kubernetes, I wanted to explain the architecture of the main alternative, which is to run Spark on Yarn. This graph, not super great quality, but basically Yarn is the resource manager from Hadoop. And it consists of a master node and a Yarn resource manager. And related to that, you're going to pick some global Spark version. So one of the big differences with Kubernetes is that with Kubernetes, a single Kubernetes cluster, you can have different Spark applications with different Spark versions within. But here you pick a global Spark version. There's also the risk of sharing some libraries. So that's where you lose a little bit of isolation between different Spark applications running on the cluster. So for that reason, sometimes people recommend transient cluster, which is like what Amazon EMR does. Like it would spin up an EMR cluster, then you run your job, then you could turn down the EMR cluster. But then that adds a little bit, a significant amount of time to set up the infrastructure. The second thing is that, Yarn was kind of designed before all the cloud native and and Docker popularity. So there is no native Docker image support. Typically, how people install their dependencies is either by actually installing jars at runtime or by modifying the AMI, so the image of the machine on which they run, which is a bit more work, a bit more painful. And finally, there is some overhead from Yarn. There's also overhead on the Kubernetes side, but I would say Kubernetes has been optimized for having a very small footprint, while Yarn actually runs a JVM on each node. And so that does consume some resources and sometimes can make starting Spark application a little bit slower. Now, on the Kubernetes side, what do we have? Basically, when you run a Spark application on Kubernetes, you're going to do, for example, a Spark submit that talks to the Kubernetes API server, which is part of the Kubernetes master. And then you're going to have pods, which are basically Docker containers running on the Kubernetes cluster. There's going to be first, the Kubernetes master is going to start a Spark driver pod, and then Spark driver is going to talk again to Kubernetes to say, oh, I need 3 executors, and then Kubernetes is going to schedule the 3 executor pods. And once you have all of that, well, the driver is going to start running tasks on the executor. So some of the differences is that now you have native Dockerization, meaning all these pods, they're basically Docker containers, and you control the Docker image, which can make it more easy to manage dependencies. The second big difference is that within the Docker image, you have the Spark version itself. So that means that on a single Kubernetes cluster, you could be running a mix of Spark 2.4, Spark 3.0, Spark 3.1 applications. You also get perfect isolation, and so it is a good practice actually to mix very different applications all in the same Kubernetes cluster. You could be mixing production and non-production, streaming and batch, et cetera, et cetera. And finally, the other big benefit of Kubernetes is that it's a very standard cloud architecture and also cloud agnostic, which means obviously it'll be easier to port your Spark application from a cloud to the other if you're already running them on Kubernetes. And you'll benefit from the Kubernetes ecosystem in general. For example, you could run non-Spark applications on the same Kubernetes cluster where you run your Spark apps. So that's really one of the main benefit, actually, is that you stop using different tools just for big data, and you start embracing the tools that the rest of your company are using. Quick recap of the Spark on Kubernetes journey. Initial support for running Spark on Kubernetes was added in 2018, but it was really bare bone. I would consider from Spark 2.4, it became somewhat production ready in the sense that, companies started using it in production. And even today, we have some of our customers run Spark 2.4 pipelines on Kubernetes, but it got even a lot better in the next versions of Spark. Without diving too deep on some of the features that I mentioned here, these are features that are specific to Kubernetes. So for example, in Spark 3.0, you had the ability to enable dynamic allocation so that you add and remove executors dynamically at runtime. In Spark 3.1, Spark on Kubernetes was officially declared generally available. So like the Spark community really considered it to be production ready. And so there were some other pretty interesting features around the ability to gracefully shut down an executor. I'll show you later in the slides what that means. And recently, in Spark 3.2, there were other performance improvements, for example, when writing to S3, as well as an improvement about how to use PVC, which are persistent volume claim, which is a type of volume, a type of disk that you can attach to your Spark executor pods. One note, just one shout out to a project that was really huge in terms of facilitating the adoption of Spark on Kubernetes. It was originally developed by Google, but it's not actively maintained by Google, and it definitely works by any platform. It's the Spark on Kubernetes operator, and basically it lets you manage Spark application on Kubernetes as a Kubernetes native object. So you can just submit an app by doing kubectl apply. You can read the logs using specific commands and so on. It provides a lot of ease of use, and so really I would recommend that. Maybe the only downside is that it is an open source project, one more that is maintained, and so it will require running a long running pod, and it will require sometimes updating it. But still, I would say it definitely simpler to use that than to use Spark Submit directly. Maybe to recap this section, what are the main motivations for running Spark on Kubernetes? Is that it's going to be a single infrastructure layer for your entire tech stack. So Spark is not going to be managed with different tooling as the rest of your stack. You're going to get a better development workflow. I'm going to show you that. Lower cost and lower vendor lock-in. And I would also say maybe a better long-term technology bet, in the sense that now most of the new deployments of Spark are on Kubernetes rather than Yarn. Maybe on the cons side, I would say that if you run Spark on Kubernetes open source, there's a lot to set up, a lot to maintain. So this is why there are managed platforms. And so EMR has some basic managed platform on top of Kubernetes, Dataproc also, but it's very rudimentary. It's missing a lot of basic features around monitoring, around management. So it still puts a lot of burden on users. And yeah, I don't think data teams should become Kubernetes experts. So this is why we built data mechanics, now called Ocean Spark, and to make Spark on Kubernetes more developer friendly and also more cost effective. But I'm not going to focus so much on the product. Still going to talk more about really even Spark on Kubernetes in general, whether it's open source, whether it's on another platform. I first want to tell you a bit about what the developer workflow looks like, given that now you're going to be working inside Docker containers, and that changes a lot of things. So first, Docker images can contain all your dependencies. So they can contain Spark itself. They will contain some version of Python, some versions of Java, Scala, Hadoop. And then you can add a lot of things. And to actually make things simpler for our customers, but even the Spark community in general, we actively built and maintain a fleet of Docker images which contain a bunch of dependencies. Like they contain libraries that let you talk to S3, the libraries that let you talk to Google GCS, Azure Data Lake, Snowflake, Delta, and more. And so whenever there's a new version of Spark or a new version of Delta, we first test that it works, and then we release a set of new images. So if you go to Docker Hub, whether you're a customer or not, you can download these images, and I think they're a great base to get started running Spark on Kubernetes. Once you have your base image, then you're maybe just going to add some code on top, like some libraries that you've developed, or read the code that you're working on. And then what's great is that you can run that maybe locally, like on your laptop or on a single machine that's dedicated to development and testing. And that can be useful typically, for dev and testing. Or you're going to be able to push that image to a container registry and then run it on your Kubernetes cluster, and it's going to be exactly the same environment. Okay, so if something works locally, it will work exactly the same way on the cluster. So there is no bad surprise between dev and prod. Another advantage is that you will not be downloading dependencies like jars and Python libraries at the last minute at runtime, because that takes time and that's a bit of uncertainty. Oh, sometimes Maven is down, and so it doesn't work. But here, you don't have any dependency on Maven. You build all your dependencies once at build time, and then you can run it many times without having that additional risk. Finally, it's easy to integrate into CI/CD pipelines. So typically what we see our customers do is that whenever they merge, for example, the pull request on GitHub, it will trigger an action which will build a new Docker image, which will tag it with the commit hash, push it to the registry, and then maybe run tests, like integration tests against it. or just make it available so that, oh, whenever you made a PR, you can run a commit with your latest code. So that's super powerful. And all these images that you've pushed, they provide really an audit log of what ran. So if you keep them, for a while in your container registry, you can go back in time and understand, oh wait, why did this fail? It's really powerful. While on the if you're using Yarn, a lot of people using Yarn will just modify their environments using scripts, bash scripts, which are very painful to debug. So these are some of the benefits of the new workflow. And I should also say that this workflow is really fast, because once you build your first image, Docker works by having a notion of layers. And so when you just make a small code change, like you're iterating on your code and you want to run the new thing, it's really fast to run. Whether you're running locally or whether you're running in production, you can get your iteration cycle under 30 seconds. Yeah, here's just to make things concrete, an example of what your environment could look like. So, locally, let's say you're using PySpark, this is what your directory could look like. So you have a Docker file, which is an instruction to build a Docker image. And then, for example, you have your main application file. You have a requirements file, which is going to list some libraries that you want to install, like pip libraries. And you have your own custom module of maybe a library that you use within your company. And then in the Docker file, so you're going to start from a base image, one of the base image that we publish, for example. And then you're going to pip install the libraries that were listed in the requirements. You're going to copy the code that you were currently working on, and that's it. Now all you need to do is build a Docker image, run it. You could run it locally, like here in that command. I'm actually running this on my laptop. Or you could run this on your cluster. This is an example of what it would look like to run this on Ocean Spark, where basically you actually need to make an API call on our public API, and you specify the image as one of the inputs. But if you were, I don't know, running this on Spark and Kubernetes open source instead of an API call, maybe this could be a kubectl apply or something like that. So I hope this was useful to illustrate what the developer workflow looks like and why it's indeed developer friendly. Now I want to talk a little bit about cluster management and what are some of the issues that you might run into, or some of the challenges that you need to address to be successful with Spark and Kubernetes. So we're going to talk about pod sizing, about automatically scaling the cluster, and about using spot nodes. So first, sizing your pods. So your pods are containers, and you need to tell Kubernetes how much memory, how many CPUs they should have. The most common mistake you can make as you get started is, like, let's say that you have a Kubernetes cluster with nodes, so machines, that have 4 CPUs and 16 gigabytes of RAM. And let's say that now you just pretty naturally set this Spark conf where you say, I want my executor cores to have, 4 cores. You would expect this would just fit right in, but no. Actually, your pod is going to be stuck in the pending state, and you're not going to get great error messages. At least if you're using open source. On our platform, we do that for you. But okay, what is the issue? The issue is that 4 CPUs is what has been advertised by the cloud provider, but in practice, a small fraction is going to be reserved by Kubernetes or by the operating system for overhead. So you're not going to get exactly 4. You're going to get maybe 95% of that. And then maybe you have also, your company has installed additional daemon sets, additional services that run everywhere, maybe for monitoring or for networking. And so that could take additional capacity. So you have to take this into account and to actually request an amount that will fit. So maybe 4 CPUs didn't fit, but 3.4 CPUs would fit. And so that's what you need to pass for the app to run. This is one of the things that we solve in Ocean Spark, in the sense that we know exactly how many resources are taken by Kubernetes, are taken by your daemon sets, and so we're going to set this value automatically for you. But that's one of the things that, you know, if you try to get started manually, you might need to go back and fix it. I'm not even explaining memory here, because memory is even a bit more complex, because actually memory, this amount is the JVM memory, but then there's a container memory limit, and so it's a calculation that's a bit more complex, but it's the same thing. Basically, you need to set it to just the right amount. If it's too much, it's not going to fit. If it's too little, you're going to be wasting space. So that's something to pay attention to. Maybe moving to a different topic, we talked about the size of pods. Let's now talk about scaling pods, and actually scaling even nodes. So adding nodes to your Kubernetes cluster. Because obviously, when you run in the cloud, you don't want to have a fixed size Kubernetes cluster with 100 nodes running all the time. You want to automatically scale, so add new nodes when you have Spark applications that need them, and remove nodes when they're unnecessary. So this is, for example, what your nodes could look like. You could have maybe a single central node using a small instance that runs 24/7, and that supports certain pods that need to run 24/7, like the Spark operator or like an ingress controller. And then you're going to have additional nodes that will be actually used by Spark pods, and that will be dynamically provisioned. So like here in this example, I have one node using an on-demand instance with 2 Spark driver, and then I have 3 nodes, each of them holding 1 executor. So the problem is, yeah, how do you do that? How do you get to that architecture? So if you use open source tooling, it's possible, but it's a bit of work. One possibility is to use an open source project called the cluster-autoscaler, and then you need to define labels on your nodes to actually say, oh, this node group will be made of instances that are R5D 2x large, and will be made of instances that are on spot. So you have to create autoscaling groups and add these labels to your autoscaling group. So, oh, I have one node group, which is on this instance type and which is using spot. And then in your Spark application, when you define what you want for your Spark driver, you're going to say, oh, I want to target this label, lifecycle on demand, and this label, instance M5 large. And so that's gonna be used as a filter, as a requirement. The Kubernetes is going to be like, okay, then I need to put it in this specific, autoscaling group. Oh, it doesn't have any node. Okay, I'm going to request a new node from Amazon. So yeah, it's doable. It's a bit of work. That's why, in our platform, we actually do this automatically for you, and we just expose these fields in our API so that you don't need to build and maintain these groups, and we just do it for you. Looks like all right. Looks like maybe this, yeah, I just wanted to mention another type of problem, but it looks like, oh yeah, I had a duplicate slide. Anyway, third and last type of problem I wanted to illustrate is how to use spot nodes successfully on Kubernetes. So as you know, spot virtual machines are much cheaper, up to 90% cheaper than the on-demand price. So it's really worth to make use of them. And Spark can make use of them really well. But obviously the issue with Spot is that first, you're not guaranteed to get them when you ask them. Maybe there is no capacity. And even once you get them, maybe the cloud provider is going to take that node back. And so that's what we call a spot kill. So in the middle of your job, it gets spot killed. So first with Spark, there's 2 types of pods. There is the driver, which is the brain. And if you lose your brain, then the entire application fails. And then you have many executors, which are doing the hard work. And here, Spark can recover from losing an executor, but it will obviously have some side effect because the executor was running some task. So first, the the currently in progress task will be lost. They will need to be scheduled on another executor and start from zero again. And more importantly, the executor might be storing files that are really the output of previous work, previous tasks. In Spark, we often talk about shuffle. Shuffle is when you exchange data across executor. So on each executor, you're first going to write different shuffle files, and then, so that's called the write side of the shuffle. And then on the read side, the executors are going to pull the files from somewhere else, and this is how you can, for example, repartition your data set according to a new key. Obviously, it means you transfer the data across the entire cluster. So when you do something like that, which is very common in Spark, you're going to produce all these files, and these files, they're really the output of previous work. So you don't want to lose them. And so when you lose a Spark executor, you're going to lose these files, and we will need to recompute the previous work. So as you can see, there are some reliability issues. Spark might still finish, but it's going to lose a lot of time. And if too many spot kills happen, maybe it could still end up failing the Spark job. So what are the solutions here? I mean, they're not super easy. First is I mentioned that, that the driver should be on demand and the executor should be on spot, right? You don't want to put your driver, which is the brain, on a spot node. And then what you could do is try to play on multiple spot markets. So, rather than putting all your eggs in one basket and asking only nodes of the M5 X large family in US East 1A, you could spread your workloads across a different availability zone, maybe a different family, maybe a different instance size within the family. However, there are some limitations. True, these are different spot markets, but within the Spark app, you should not spread across AZ, because that will actually that will decrease the performance, because you will be sending data across AZ. And regarding family, you should pay attention to different instance families don't have the same memory to CPU ratio, and so Spark pods should be sized accordingly. So this is actually something that we do for you at spot.io and Ocean Spark. And this is not something that other platforms do well at all. I really think this is where we have a unique technology. So there's a lot of info on this slide, but I just want to show you what our API kind of looks like and how it would translate. So in our API, let's say you submit two Spark applications, a blue and an orange one. And let's say that for the driver, you say, I want to target instances of the M5 family. And your executors, you want to target instances of the R5 family. And the driver will be on spot, but the executors will be on, the driver will be on demand, and the executors will be on spot. And so we're going to take these requests. We're going to see, okay, we have two driver. Both of them can fit on a single M5 large on demand. So let's get the smallest instance and run it there, to not waste capacity and increase your costs. And then on the executor side, what we're going to do is we're going to look dynamically right now when you submit your Spark application. What do the spot market look like? Which are instances available in X large, in 2X large, in 4X large? What is the spot price? And then we're going to optimize. Okay, it looks like we have a lot of instances in the X large and 2X large, but the 4X large are expensive, or there is no capacity. Spot knows how to do this because they have customers worldwide on the 3 clouds in all the region, and so they know dynamically what the spot markets look like. And then instead of putting all your eggs in one basket, they're going to spread also the workload across multiple family, so that maybe this app is going to run for 3 or 4 hours, and at some point there's going to be a tension in one specific market, and you might lose the R5X large. But the good news is, since you spread your workloads, you're not going to lose all your executors at once, and so the impact is going to be minimal. And obviously the beauty here is that the executor pod size doesn't change, right? It's still 4 cores, but we will do the math for you, and we will automatically figure out how to spread this and how to bin pack the thing efficiently. That's not something that can be done open source. So so unfortunately, if you stick to open source, you will need to do something a lot more simple, and you will need to suffer the consequence of what happens if my spot nodes are not available. I hope this was useful. I saw there were some questions, and I'll get to them. Thank you for the question. I think I'll get to it a bit later, just because I want to be respectful of time. I know we're already 35 minutes in. I just want to mention, one last thing about cluster management. I also mentioned that there were shuffle files, and shuffle files are precious, right? Because they represent past work, and so you don't want to lose them. So what happens if a spot kill happens? Can we save the shuffle files? So yes, there's such a feature that was implemented in Spark 3.1. It requires some integration with the cloud provider, so it's not something you get entirely for free, but we tested it and it works. So what the cloud provider do is most of them, all of them, give you a termination notice, meaning before, like Amazon, I think before killing a spot node, will tell you 2 minutes early, I'm about to kill this Spark node, this spot node. And so here, by installing a certain node termination handler, we can hear that. So we can be warned, okay, this node is about to die. And then what's going to happen is that we're going to proactively move the shuffle files. So we know this executor is about to die, but we know this executor isn't. And so we're going to move the shuffle files from here to there. The other thing we're going to do is we're also going to stop scheduling new tasks, because we know it's not worth it. This executor is about to go. And so yeah, the consequence is that yes, the executor is gone, but the shuffle files are saved. The driver has kept track of where the shuffle files are, and so the job can continue unimpacted. You won't need to recompute these precious files. So that's a feature that's called graceful executor shutdown that's available from Spark 3.1. Great, we're almost at the end, so I hope this was enjoyable and I was able to show you some of the benefits of running on Kubernetes, some of the challenges and how to solve them. You see, I made some allusion to the product that we built, Ocean for Apache Spark. It will actually be the topic of our next webinar, where it will be a deep dive into the product and including a live demo. I didn't want to cover too much on this first webinar, but basically, yeah, I did want to give you a preview so that you know what to expect on the next one. So Ocean for Apache Spark is basically a serverless Spark on Kubernetes in your cloud account. So by serverless, we mean that you shouldn't need to have Kubernetes expertise, or you shouldn't need to manage the VMs. We're going to do this for you. We're going to provision the nodes, find the right instance type for your workloads, use spot nodes when available, entirely transparently, so that we make you successful with Spark, and we also reduce your cloud provider costs. So really, I just wanted to give you a preview of what the product looked like. Obviously, you benefit from native Dockerization and from our Docker images that come, pre-packaged with connectors to all the common clouds, as well as a performance improvement sometimes in the image. It also comes with integrations with the tools from the popular data science ecosystem, Jupyter Notebooks, Airflow, and other schedulers than Airflow, Docker and Kubernetes. You can really integrate with any kind of system, whether it's monitoring, networking, security. And then finally, last but not least, we have a UI, a web UI, where you can track your application logs, your application metrics, like memory usage, IO usage, CPU usage. And you can troubleshoot and understand what is the performance of your pipeline, how to if there's an issue, where does that issue come from. And this information is available while the app is running, but it's also persisted. So really, this is saving you hopefully a lot of time, and that's one of the things our customers like the most. And then in terms of the infrastructure, this is where there are all these optimizations that I mentioned. So we take care of scaling the cluster up and down at runtime based on load. We take care of optimizing the type of instance based on the spot market dynamics. We also enable application scaling within Spark, where a running Spark application can decide to add or remove executors based on the load. And we also tune, so we also optimize some Spark configurations for you. Typically the size of the containers, like I mentioned, how much memory and how many CPU for each pod, the number of Spark executors, the number of partitions, some Spark configurations around shuffle, and some Spark feature flags. So really the goal here is it's not black magic. It's really, it's more as if it's using the same rules that any data engineer would use, but it's scaling it, it's automated. And so it works even if you're running hundreds of thousands of pipelines every day on the platform. And that's where you see a lot of the cost savings, because really our goal is that if you're coming, say, from Amazon, from running Spark and Kubernetes yourself, or from a competitor, we should prove you that when you look at your total costs, even though we are a managed service and we charge you a fee, your total cost should go down. And very often we see even total cost reduction in the 50, 60, 70% or more. Yeah. Anyway, next week, or actually next month, we'll have a webinar where we do a deeper dive into Ocean Spark. Yeah, I will not cover the architecture because I think we're actually over time. I was shooting for 45 minutes, and I believe we are there. Maybe if you guys have some questions about the architecture in Q&A, I'm happy to cover that. So I think I will now turn to Q&A. Thank you for. I hope this was useful. So let's see. I see there was a question from Niels. You mentioned memory settings for Spark briefly. I was wondering about the executor memory overhead. We noticed at our company that setting this to 0.1 works well for smaller nodes, but not enough if we use big nodes. Do you have a recommendation to change the overhead depending on the node size? Yeah. Okay, that's super interesting. Let me share my screen, because I think the easiest way for me to answer this question is to show another in particular. Here we go. I just want to explain first what is the memory overhead. So when you start a Spark application on Kubernetes, there is a memory setting, and that memory setting is actually the JVM memory heap size. So if you pass 10 gigabytes, it means that the JVM maximum heap size will be 10 gigabytes. But the container memory is actually higher. The ratio between the two is called memory overhead factor. So if you set a heap of 10 and a memory overhead factor of 0.4, the actual container memory is 14 gigs. Now, you need to pay attention, when you set this number. There are two types of issues that can happen. If this number is too low, meaning the JVM maximum heap size is close to the container memory limit, what you will sometimes see is that if the JVM needs a lot of memory and grows to its maximum heap size, sometimes you may get a container out of memory error. So Kubernetes, actually Docker, you won't respect the memory limit. Let's say it's 14 or it's 11, and Kubernetes will kill you. You're saying, wait, why? I'm running Spark, it runs in a JVM, the max heap is 10, how come I'm using more? First, the JVM always use some off-heap memory for its internal stuff. You can also configure Spark to use off-heap memory, but so there's a trade-off. And if you run anything PySpark, sometimes there will be Python processes in the container that can also consume a significant amount of memory. So for this reason, we actually recommend, I know the default is 0.1, but we actually recommend a higher default. For Python, we recommend 0.4. It could be sometimes a little more. And for Scala, I would recommend at least 0.2. So that's one type of issue. The second type of issue is that yeah, it will impact your container size, and so it will impact how the containers get bin packed onto a node, right? If you computed your heap so that you think you're going to get 2 containers to fit onto a node, and now you increase your memory overhead factor, each container is going to be bigger, and it's not going to fit anymore. So that's another thing to pay attention to. With respect to your point, like you said, the container memory creates more issues when you're running on small Kubernetes node rather than on large Kubernetes node. It may be indeed an issue that, let me go back to a slide that I've shown earlier. The percentage of resources that are going to be used by Kubernetes system daemons is going to be higher proportionally than if you're using a very large instance, okay? Because it's not computed as a percentage, but it's usually almost fixed amount. So this is where maybe you see a difference that when you run that on a small instance, there is less available within some capacity is used, a higher share of capacity is used by the OS. And so maybe you're getting memory kills because at some point, the container tries to request a bit more, and actually the OS says no, and then you get an out-of-memory error. So what I would recommend on average is to indeed on Kubernetes, most people tend to use bigger nodes, so don't go necessarily for the smallest nodes or 2 cores and 4 cores. And I would also recommend to increase the memory overhead factor because it's often an issue. Let's see, is there another question? Melissa, how does Spark dynamic allocation work on Kubernetes where there is no external shuffle service? Yeah, great question. So dynamic allocation is the ability for Spark to add or remove executors dynamically at runtime. Maybe let me show you the slide to help answer. So you're going to be able to add or remove executors. Adding executors is always safe. Removing an executor can be an issue, right? Because you've written some shuffle files, and so you don't want to lose these shuffle files, just like you don't want to lose them during a spot kill. So what can be done? In Spark 3.0, there's a feature called shuffle tracking. So you have to enable it to run dynamic allocation on Kubernetes. And so the driver will keep track of which executor is storing shuffle files. And so these executors will not be removed. So you can enable dynamic allocation. It's just that shuffle files will not be removed. So sometimes an executor might continue running even though it's not necessary. In Spark 3.1 and Spark 3.2, you could get rid of that either by using the feature that I mentioned here, where you can move shuffle files, or by using yet another feature from Spark 3.2, which is called PVC reuse. I think it's a bit advanced to go over this now, but there are solutions. So TLDR, even though there is no external shuffle service, it's not necessary, you can enable dynamic allocation. And I would really recommend dynamic allocation for workloads that are not super stable. So typically notebooks, anything interactive, and sometimes some streaming, some long-running workloads where you want to add and remove executors dynamically. Great. So I had two great questions. If you want to dive deeper, first you can always connect with me on LinkedIn. Just search for my name and we can chat. On our next webinar, we're going to do a deep dive into Ocean for Apache Spark, the product, including a demo. So register for it. And if you don't want to wait until the next webinar, but want to talk with our team soon, you can use this link. It should be part of the slides that will be sent, and schedule a time with us. So I hope this was useful. I think I'm gonna stop now, but I wish you to have a great day, and yeah, send us some feedback. And yeah, enjoy your time. Be successful with Spark and Kubernetes.